Good afternoon, everybody. We'll go ahead and get started since it's just 12 o'clock. So test 5 is on Friday. Any questions? No? Okay. I guess no surprises, 5 tests in. So last day we talked about the magnetic field around long currents of wire. We took our wire and we formed it into a loop, and we started to talk about what was the magnetic field due to that loop of wire. We had to stop partway through, so we'll just do a very quick refresher. So we had our loop of wire, and we talked about the symmetry, and I put the ring up on the board, and I brought down my meter sticks with vectors on them. And overall, we used the right-hand rule to look at the direction of the magnetic field made by each bit of wire. We saw that the Y components would all cancel, the Z components would all cancel, and we were left with just the X components. So if we want the net magnetic field, we have to add up all the X components, and our total magnetic field after we add them up is going to be in the X direction. So we got that much done on Monday, and then we started to get into the process of solving it. So we said our X component of the element of the magnetic field is just the total field times cosine theta, because the X component was adjacent to that dB. We recognize that this is the magnitude of dB, because we've already settled on our direction. To get the magnitude of dB, we use our Biot-Savart law, mu naught 4 pi I and r squared. Those are all scalars. So we need the magnitude of ds cross r hat. So that's the magnitude of ds, the length of one little element, times the magnitude of r hat, that's a unit vector, so it has a magnitude of 1, times the sine of the angle between ds and r hat. So ds is along the loop, r hat is towards our point, and if you look at those two, they're perpendicular, so that angle is 90 degrees. So we got down to dB was mu naught over 4 pi times I times ds over r squared. So that's where our time was up, and we had to quit. We'll keep going from here. We'll put this expression in for our dB, and we'll try and solve this problem. And I posted all these slides with Monday's class. I'll post them again with today's class, just so you have a complete set there in your notes. So we'll pick up from right here. So our net magnetic field B is the integral of dB, which is mu naught over 4 pi times I times ds divided by r squared times cosine theta, and we know it points in the x direction. So we'd like to do an integral. Before we get going on the integral, let's see if we can figure out what does r stand for and what is cosine theta. So let's simplify our variables a little bit here. Pull the picture back down. If we look at the picture, r is the hypotenuse of a right angle triangle where the legs are x and r. So we can calculate that little r value. So from the diagram, r squared is equal to x squared plus r squared, or r is the square root of those guys. So that's our r. So r is the distance from your element ds to the point where you're trying to calculate the magnetic field, your point P. Next we have cosine theta. Cosine theta, and we thought about all those angles. We labeled this one as theta, so this one was theta. Cosine is adjacent over hypotenuse. It's the radius of the circle divided by our little r. So there's some bits we can put into our equation. We'll put those in next. So then our b is equal to the integral mu naught over 4 pi times I times ds r squared, we'll just leave that as r squared for a moment, times r over r. R squared times r, that's just r cubed. So we'll put that bit in. Now we'll substitute r is x squared plus r squared to the 1/2. We have to cube this guy, that goes in our denominator. Almost to the end. Because it's an integral, we can take all of our constants out front of the integral, and we'll see what our integral is going to turn out to be. So mu naught is a constant, I is a constant, r is a constant, 4 and pi are constants, x is a constant, x is our distance along the x-axis. We're trying to find the magnetic field at this specific point P. So in the middle of our problem, this x is not going to change. X is constant, so x squared plus r squared can come out from our integral here as well. So we've got the integral ds I hat. So what is this integral going to be equal to? So the integral of ds means we're adding up all the little bits of ds as we go around the circle. What do we get if we add up all the little pieces of ds? Get the circumference of the circle, right? So we add up every little length around the circle. We end up with the total length, which is just the circumference. So 2 pi times the radius for the integral of ds. Okay, let's get that into our answer. Mu naught times I times r times 2 times pi times r divided by 4 times pi times x squared plus r squared to the 3 over 2 I hat. Not the end of the world if you leave it looking like this, but we can simplify it a little bit. Pi on top, pi on bottom, so they divide out. 2 on top can go into the 4 on the bottom, leaving a 2 in the denominator. So we can simplify that a little bit. So that gives us with our final expression for the magnetic field at some distance x from the center is equal to mu naught times I times r squared over 2 times x squared plus r squared to the 3 over 2, and that's in the x direction I hat. So there's the magnetic field on the axis of the coil, and it points in the x direction. Okay, any questions here? There's a couple of interesting things you could ask about this. So when you get a result finding the magnetic field on the axis, so at some point x here, the two places my mind always goes is what's the behavior when x is 0, what happens at the center, and what's the behavior when x is big, what happens when we get far away from the center. So let's look at those two limiting cases next and see what they look like. So case number 1 we'll look at, what happens at the center? Center of the ring means x equals 0. So this one's not hard to figure out. X is 0, we'll put in x equals 0. So our magnetic field B is mu naught times I times r squared over 2 times r squared to the 3 over 2 I hat. R squared to the 3 over 2 is r cubed. Got r squared on top, r cubed on the bottom. That leaves us with an r on the bottom. So there's our magnetic field at the center of the ring. We see that it points to the right, and that makes sense if we want to come back to our right-hand rule. So in our right-hand rule, when you have the magnetic field around a wire, you put your thumb with the current and your fingers make circles showing the direction of the magnetic fields. So let's think about this piece of wire. We put our thumb in the direction of DS. Our fingers make circles. We see they're pointing out from the center, so that direction makes sense. It lines up with our right-hand rule. So that was our case 1 at the center. Case 2 is what do we get if x equals a big number? We'll say far away, and what we mean by far away is x is a good bit bigger than the radius of the circle. So that's our definition of far away. So if x is a fair bit bigger than r, let's see, we need our equation back. So here's our equation. The place where x comes into play is the denominator. Let's see what happens to our denominator if x is pretty big. So if x is much bigger than r, then x squared plus r squared to the 3 over 2 is about equal to x squared to the 3 over 2 is about equal to x cubed. So in our denominator, x is so much bigger than r, then you can treat r like 0. Okay, you get a similar behavior. So x squared plus r squared to the 3 over 2 is about equal to r cubed. So let's see what that does to our equation. So our magnetic field B then is about equal to mu naught times I times r squared over 2 times x cubed. And that's in the x direction. So with this I times r squared, this kind of gives me an idea. We defined magnetic moment as current times area, I times pi r squared. That makes me think about this. So I'm going to multiply the top and bottom of this equation by 2 pi. So that gives me mu naught times 2 times I times pi times r squared, divided by 2 times 2 is 4 times pi times x cubed, and that's in the I direction. Okay, so this was artificial. I multiplied by 2 pi on purpose just to get that form. So this bit right here, pi r squared I hat, that's the area vector. I is the current. So this piece altogether is the magnetic moment, mu. So that was a bit we defined a couple of classes ago. So that was the magnetic moment vector, and we talked about that in terms of when we were discussing magnetic torque. Torque is mu cross B. So we'll put our magnetic field in terms of this. So we get 2 times mu naught times the magnetic moment vector divided by 4 pi times x cubed. So this magnetic moment was also called the magnetic dipole moment. So this shows that little loops of wire act like magnetic dipoles. The little loops are magnetic dipoles. What's kind of interesting here is this, in fact, is a general result. We kind of made it a little bit artificial by multiplying by the 2 pi and getting the area of a circle. This, in fact, applies to any loop. We could do the same thing, finding the magnetic field around a square loop or a rectangular loop. We'd get the same result to work down to this part right here. And then this is a little bit similar to what we did in our electric fields chapter. So this is like our electric field around an electric dipole. That was where we had the two little charges, equal and opposite, separated by a small distance. That gave us an electric field, 2 times the dipole moment, divided by 4 times pi times epsilon naught times x cubed. So this is showing those similarities again coming back. We can find the magnetic field of a little magnetic dipole, and it's like the electric field of a little electric dipole. So electric and magnetic fields are certainly linked. They kind of have a lot in common. Okay, any questions? Yeah?
Why did you multiply by 2 pi over 2 pi instead of pi over pi?
Because I wanted 4 pi in the denominator. Because like mu naught over 4 pi just pops up all over the place, but pi over pi would work as well. Yeah, and I also wanted it to look like the electric field. Yeah, a lot of these equations are a bit artificial with the stuff you multiply by, just because physicists like things to line up a certain way. Okay, so let's move on from this bit. Is everybody finished with that? So back when I talked about torque and we talked about current loops, we said that little loops acted like magnets, and that shows us why, right? There's magnetic fields around little loops of wire, so they look like little magnets. And if you wanted to trace out those magnetic fields, there are different ways to do it. You could put some current through a wire and shake some iron filings around. That's what this picture is. So there's a little metallic loop here. They've run current through it. They shake on the metallic filings, the little iron filings, and it shows a magnetic field coming through this way. We did kind of the simplified case of what was the magnetic field right here. And I say simplified, even though it was a fair bit of work. You could use your Biot-Savart law, and you could find expressions for the magnetic field everywhere. It's just that's way more complicated, right? That's why we stuck to on axis. If you did the calculation everywhere, this is what it would turn out to be, lines that look like this. So that's how you can trace it with like little compasses or iron filings. And it makes our little loop look like a bar magnet. And that was the result we had shared before. So the magnetic field comes out of the north end into the south end. So it sort of looks like this as well. So loops are like a bar magnet. What else do we have? So this is what it looks like when we go top down on the loop. If we chose to look directly at the loop instead, so let's say we put our eyeball here looking into it, all of those magnetic field lines at the center would be coming towards us, so that's this picture, so we're looking at John. And all of the fields outside the loop would be going away from us, so that's what the field lines look like if you're looking straight at the loop, if you pick it up and look at it. Our current loops act like permanent magnets or bar magnets. If we have a single loop, that was the calculation we just did, B on axis is mu naught I times pi times r squared divided by 2 times r squared plus x squared to the 3 over 2. That's for a single loop. If we have n loops, because you rarely have just one loop, your total magnetic field would just be n times that number. So you get one field for every loop. Okay, any questions? So let's do an example. So in our example, a closely wound, and this bit is a little bit important because our next topic is going to take us to solenoids where it looks more like a slinky, like an extended pile of coils. This time they're closely wound, so it looks more like a roll of tape with all those loops on top squished together. Circular coil has a radius of 2.4 centimeters. So the radius of our coil looks something like this. So there's our coil all jammed together. The radius is 0.0240 meters, and it has 800 turns. That's our N value. No units on turns, of course. What is the current in the coil if we want the magnetic field to be 0.077 Teslas? Okay, so we want to use our equation for magnetic field. We know most of the ingredients, and we'd like to find the current. So this is just going to be kind of a plug and chug. And this is the magnetic field at the center of the coil. So part A, our magnetic field has a magnitude of 0.0770 Teslas. We're at the center of the coil, so X equals 0. So there's some additional information. We'll write down our equation. B equals N times mu naught times I R squared. 2R squared plus X squared to the 3 over 2. But X is equal to 0. So R squared to the 3 over 2 is going to give us R cubed. The squared goes into the cube, and mu naught I over 2R. Which is the same as what we did a minute ago when we wrote down the expression for the magnetic field at the center of a single loop. The only difference in the result now is that we have an N. So this question gives us B, we want I. So our current I is going to be twice the radius times the magnetic field divided by mu naught times N. So we'll put in our numbers, 2 times 0.0240 meters times 0.0770 Teslas divided by mu naught, that's 4 pi times 10 to the minus 7 Tesla meters over amps times our number of turns, which is 800, gives us a current of 3.68 amps. So if we run that current through 800 coils, we'll get this small magnetic field at the center of the coil, and then it will fall off as we go further away. Any questions there? All right, part B. What distance of X from the center of the coil on the axis of the coil is the magnetic field half of its value at the center? So this time we know that the new magnetic field is half of this guy, and we're trying to solve for the X value. So similar problem, just looking for something different here this time. So for part B, the new information we have is that B is 0.0770 Teslas, that's divided by 2, 0.0385 Teslas. There's our magnetic field. Trying to find that X value, and this time we know what the current is. So once again, we have all the numbers. This is just a plug and chug with slightly more difficult algebra. So B is equal to N mu naught I R squared over 2 times R squared plus X squared to the 3 over 2. So we'll bring our R squared plus, we'll bring our denominator up to the other side. R squared plus X squared to the 3 over 2 equal to N times mu naught times I R squared over 2 times B. So I did a little bit of algebra in my head there. Everybody okay with that step? And I just kind of confirming, because it feels like a sleepy Wednesday later on in the term. Could be easy to miss an algebra step here. Like even in second year, we can still miss algebra steps. Okay, so we're still good. All right, we're trying to dig out our X. That means we got to get rid of our exponent first, so we'll raise both things to the power of 2/3. R squared plus X squared equals N mu naught I R squared over 2B to the power of 2/3. Subtract R squared from both sides. And then to find our x, we'll just take the square root of both sides. Put all of our numbers in, and we should get 0.0184 meters, or 1.84 centimeters. I did the calculation a couple of times on my calculator, got the same answer both times, so I'm fairly confident that that is the right answer. Okay, any questions? Okay, let's do one more example. Take an odd-shaped little wire and find the magnetic field around it. So our odd-shaped little wire has a straight bit, and a curved bit right here. We're asking what is the magnetic field strength at the center of the semicircle. So we'll put a dot here, we'll call that point P, and we're going to try and find the magnetic field strength. It doesn't ask for direction, although it's not going to be hard to find direction. We know the current is flowing this way, so the direction can be given by the right-hand rule. So we could find direction certainly, but we're not asked for it. So if I look at this wire, and I want the total magnetic field, my mind breaks it into 3 bits. I've got a section here, so section 1. I've got my curved section, I might call that 2. And I've got my next straight section, I might call that 3. If I find the magnetic field due to each of the 3 sections, add them up, it's going to give me the total magnetic field. So our net magnetic field B is going to be B1 plus B2 plus B3. And we'll use our Biot-Savart law 3 times to find that magnetic field. So the magnetic field is mu naught over 4 pi I times ds cross r hat divided by r squared. So we're going to do that 3 times, find the net magnetic field, and add them all up. So I'm going to do section 1 first. So B1. I'll redraw my wire, which is hard to draw on top of the diagram. So there's my wire. I want to do my integral. I need to identify a little bit of the path ds. So I'll pick out a little bit of my wire. It's got the same direction as the current, so that's to the right. So there's my ds. Trying to find my magnetic field at a point P, which is a distance of r away from the end. So when we do finding our magnetic field, this vector r is from our ds to our point P, so this is r. And r hat is our unit vector that points from our ds to our point. Everybody okay with the diagram? So it's important that you identify ds, that you identify r, and you identify r hat, because if you don't have all those relative directions, you can't figure out the cross product. So then if we figure out our magnetic field, we know it depends on ds cross r hat. Let's do that bit first. ds cross r hat is I cross I equals 0. Those two are parallel. ds cross r hat is 0, then our magnetic field B1 is also equal to 0. Okay, so no magnetic field right there due to that wire, because it's right on the end of the wire. Now that I've got B1 done, I'm going to go ahead and do B3, because I think I'm going to get the same answer. So I'll do B3 next while I'm thinking about that. So here's my wire. Here's my point P. This distance is r. Pick a little bit of my wire. There's ds. My r goes from my ds to my point. So there's r. And my r hat goes from my ds to my point as well. So this time my ds is to the right, my r hat is to the left. those are anti-parallel. ds cross r hat is still 0. So then my magnetic field B3 is also 0. Okay, so B1 and B3 were pretty easy. Looks like the bulk of our work is going to be in finding B2. It shouldn't be too hard because we've already done that circular geometry, but we'll go through the process again. So for B2, we've got our little loop, half of a circle. We need to identify, we're trying to find our magnetic field right here at point P. Have to identify a little bit of the wire ds going in the direction of current, so there's our ds. Our r is from our ds to our point, so there is r, that's equal to the radius of the circle. So r equals r. And r hat is from my ds to my point P. So I've got ds identified, I've got r hat identified. To find my net magnetic field, B2, it equals the integral mu naught over 4 pi I ds cross r hat over r squared. Let's work this part out. If I want the magnitude of B2, I want to use the magnitude of ds cross r hat. The magnitude of ds cross r hat is the magnitude of ds times the magnitude of r hat, that's 1, times the cosine, sine of the angle between them. Those two things are perpendicular. Sine 90 degrees equals this. Okay, so I've simplified my ds cross r hat. So my B2 is the integral mu naught I over 4 pi ds over r squared, that's the radius of the circle. You can take my constants out front of the integral, mu naught I over 4 pi r squared integral of ds. This is something we did in our previous problem. We had the integral of ds. That time we went around the full loop. This time we're going around a half a loop. So the integral of ds will be our length around a half of a loop. It's going to be a half of a circumference. So there's our integral ds, we'll put that in. Mu naught I over 4 pi r squared times pi r gives us the size of that magnetic field B2 is mu naught times I divided by 2 pi. Oh my goodness. Sorry, I divided 1 by 4 and I got 2. Try that again. So the size of our magnetic field B2, pi's cancel, one of the r's cancels. We've got mu naught times I over 4 times r. Our previous result, this is probably not a surprise in light of the previous result. When we had the full ring, the magnetic field was mu naught I over 2r. This is half that because it's half of a ring. Okay? So no surprises there. To get our direction of the magnetic field, oh wait, let's do our magnitude first. So the net magnetic field is B1 plus B2 plus B3 equals mu naught I over 4r. To get the direction, let's use our right-hand rule. So the magnetic field makes big circles around the wire. So this is part of our loop. The magnetic field is making big circles. So my pen represents the ds. I want the magnetic field right here. I put my thumb with my current or my ds. And I ask, what is my hand doing right here? So So your thumb goes with ds, and you're asking what are your fingers doing at point P? They're pointing into the page. So my magnetic field vector, because if I were asking this on a test instead of just picking an example from the book, I would certainly ask for the whole vector, not just the magnitude. And we get that direction using the right hand rule. Okay, any questions? So what we've been working on for a little while now, like a couple of classes for sure, is we've used the Biot-Savart law to find magnetic fields around moving charges and current carrying wires. And for doing those, we mostly use an integral. You may or may not remember, because it feels like a long time ago, we did that with electric fields too, right? We said that electric field due to a point charge is kq over r squared. Due to continuous charge distributions, it was the integral of k dq over r squared. We did that for a lot of different geometries, and we got a lot of different results, and then we moved on to Gauss's law. And what we said with Gauss's law is that the net electric flux through any closed surface, so a three-dimensional volume, a surface, was given by the net charge inside that surface divided by a constant. And what this gave us was a tool to find electric field when we had high degrees of symmetry. As long as we were able to do this integral, right, as long as it wasn't too hard, you know, something along a line, something along a circle or a cube, we can do those integrals, and we were able to find electric fields. We have a similar thing in magnetic fields, and that's called Ampere's law. So we're going to get into Ampere's law next. And so Ampere's law is our next bit. Ampere's law tells us that the total magnetic field around a closed curve, so right here we're different from electric fields. Electric fields, we're going through a closed surface. That's a 3D thing. This one is around a closed curve. This is a 2D thing. So the net magnetic field around a closed curve, and we write that as the integral of B dot ds. We put a circle on our integral to tell us that it's the path around an entire closed loop. And ds is our path for our curve. So this net integral of the magnetic field, it's a direct result of how much current is inside that curve. So just like Gauss's law, the charges outside didn't matter. Ampere's law says the current outside doesn't matter. It's only the current inside. So this is equal to mu naught times the current enclosed by the path. So we normally write I with the word I in next to it. So we're going to use Ampere's law to find magnetic fields. We've done some of them by integrating. It can be difficult. And we can use Ampere's law to find it quickly, as long as we have lots of symmetry. Okay, so there's our goal. It's kind of like the two-dimensional version of Gauss's law. So our Gauss's law was a 3D thing. This is a 2D thing. So for our first example, we did the magnetic field around a long line of current, and we did that with the integral. Next, we're going to do it using Ampere's law, and we'll see that we get that result quite a bit quicker. But one of the deals is, just like when we used Gauss's law, we had to know what the electric field looks like. We had to know what the symmetry was. Same deal here. We have to have an idea of the magnetic fields and those, which way it points, and to use that symmetry. Okay, so we're going to use Ampere's law to confirm this result we got by integrating. So as we get started, our Ampere's law says that the integral of B dot ds, the first thing we need to figure out is what do we choose for our path. The path is really important. So we know that the magnetic fields around current carrying wires make big circles around the wires. We always pick our path to match the symmetry of our magnetic fields. If the fields are circles, our path is going to be a circle. So for our path, we want it to match the magnetic field B, which means that our path is going to be a circle. We'd like to find the magnetic field at some point P, so our circle is going to cut through point P. The wire is going to be at the center. Our path is a vector. It needs to have direction. The direction of the path is going to be the same as the orientation of the magnetic field. So just like in Gauss's law, we picked our Gaussian surfaces to match our object, to match those symmetries. In Ampere's law, our path is going to match our magnetic fields so we can take advantage of the symmetry. So if we're talking about a long wire, we want to pick our path. We're going to take our path to be a circle around the wire. I'll draw that with a dotted line. I'm going to say that the current in my wire flows up. So there's my current I. So this is my path. That's my total path S. The orientation, your thumb goes with your current. Your fingers show the orientation of the field. So the path is coming around this way, to the right in front and to the left behind. When we do our integral, we know we're going to want some little bit of the path ds, so we can show that on our picture as well. So a little bit of the path ds looks like this. It can be hard to always draw in 3D, so you can take a top view if you prefer. So if we look down at the wire, the current is coming out towards us. Our path is coming around in a circle. The wire has to be at the center, the path has to cut through P, the orientation has to match the magnetic fields. So this is our path S. We can identify some small element of our path, ds, that has to match the orientation too. And we might throw in that the distance between our wire and our point is r, because that's going to become important. Okay, so there's our picture. When you're doing these problems, you always have to show the path and show the element of the path. Those things are really important. Our Ampere's law has two sides on the equation. We have to figure out what is B dot ds. We have to figure out what is the current inside. We'll put the two things together and we'll find our magnetic field. So for the left side of our equation, the integral around the closed path, B dot ds, going to be the integral of the magnitude of B times the magnitude of ds times the cosine of the angle between them. We purposefully picked ds to be parallel to B, so the angle between them is 0. Okay, and a little bit of shorthand here. It looks like an 11, but I said 0 degrees, comma, parallel. So 0 degrees because the path and the magnetic field are parallel. So that's where that 0 degrees comes from. So cosine of 0 is 1, so this is the integral of B dot ds. As long as we're a constant distance from our wire, that magnetic field is going to be a constant. So B comes out front. We've got B times the integral of ds. The integral of ds is the distance along our path. We add up all the little bits, so we get the circumference equals B times 2 pi r. So there's the left-hand side of our equation. The right-hand side is not too difficult. So this equation should have an I in on it. The current inside our path, I in, is just the current flowing through the wire. So the entire wire with its entire current is all inside the path, so current inside is current in the wire. Okay, let's put it together and get our answer. So the integral of B dot ds will be times 2 pi r equals mu naught times I inside, which is just our current I. Solve for B, we get B is mu naught I over 2 pi r. We know it's a vector, and we know we get the direction using the right-hand rule. Okay, same result, but we're only a couple of lines here. So Ampere's law can be a really quick and simple way to find magnetic fields. Any questions? Okay, I'm sure we have time for one more example, because the next one is pretty quick. It's almost the same as this example. So in our next example, and this is the sort of thing you can certainly have happen. Lots of wires are braided wires, so there's little bits of wire all coming together. 3 long, thin, insulated wires are very close together. Use Ampere's law to find the magnetic field at a point P, which is 10 centimeters from the center of that wire. So in our problem, whether we take a side view or a top view, the distance between the wire and our point is 10 centimeters. That's our distance r. The currents are, I1 is 0.5 amps up. I'm going to call this one I1. I2 is 0.75 down. I'll make this one I2. And I3 is 1 amp up. I'll make that the wire in the back, I3. Doesn't really matter which is which, but you should label them just to be sure. So we want to use Ampere's law. The integral of B dot ds is mu naught times I inside. So for the first thing we want to figure out is what is the integral of B dot ds? It means we have to pick and identify a path. We know the magnetic fields around long straight wires make circles, so our path S should be a circle. Our wire should be at the center. Our point P should be on the circumference. So we'll draw a path that matches all of those things. For the orientation, I notice that the net current points up, so I have 1.5 up and 0.75 down. So overall, more current flows up than down. So I'm taking my orientation to be this way of my path. Okay, so there's my path S. There's a little bit of my path ds. I can draw that on the top view as well. So one wire coming towards us, away from us. So, first thing we want to sort out is what is the integral of B dot ds. I'm going to say for this side of the equation, I'm going to show the steps just like we did on the previous slide. And after we show the steps, we get B times 2 pi r. For the right-hand side of the equation, I in is the net current enclosed by our circle. The net current is all of those currents added up. So I in equals plus 0.5. I'm going to call positive up. I2 is down, minus 0.750 amps, because this one is down, plus 1.00 amps, plus because this one is up. So our net current inside is positive 0.750 amps. Positive tells us that the net current overall points up. Okay, now we can just put it all together. B is equal to mu naught times I inside divided by 2 pi times R. R is given in the problem as 10 centimeters, 0.10 meters. So our net magnetic field B is equal to 1.5 times 10 to the minus 6 Teslas. Using our right-hand rule in the 3D version, our current goes up, our fingers go into the page here. And if we look at it in the top view, our current is up, our magnetic field comes around, points up in this Okay, and that does take us up to the end of our time today. So our test is Friday, and we'll do more of this stuff on Monday coming. Oh, and there's kind of an interesting talk coming up here in the next hour, so if anybody is sort of interested, you are most welcome to stay. They'd be very excited to have you.